Computer. Hello, good evening. It's October 21st. It's 6 p.m. We're all in Davis. Today, we're going to have a lecture by Wang about calibration, choice and calibration of stochastic elastic plastic material models for analysis with stochastic elastic plastic finite element. So today with me are Heshen.
Hi.
Dr. Han Yang.
Hello.
And Yusheng Yang from Tongji, who's visiting here, who's actually stuck here. You can't go. We'll talk about it. Okay, good. Thank you very much. So, Heshen, it's all yours. Start sharing your screen.
Okay.
And then we'll listen and maybe make comments or ask questions and so on. Go ahead.
Yeah, sure. So, okay, let me see.
Try to make one slide or yeah.
View mode. Presentation. Like this one, right?
Yeah, something like that. Yeah.
Okay. Yeah. So yeah, good afternoon. Yeah, today I'm going to talk about the choice and calibration of the stochastic elastoplastic material parameters. So this is following our last talk on the stochastic elastic material parameters. And so again, we were going to first talk about sorry, the material model that we are using here. So basically, we are using a vanishing elastic region elastoplastic model with a nonlinear Armstrong-Frederick kinematic hardening. So this is the 1D equation that we're going to use here. But now we're trying to consider the uncertainty in this 1D nonlinear inelastic equations. So as you can see here, you have the following uncertain parameters. You have the incremental stress on the left-hand side, and then on the right-hand side, you have the uncertain material parameter HA, which is control the initial stiffness of the yielding, and then the parameter CR. So HA over CR will control the final, the strength of the material, and then you have the uncertain, incremental strain that will be driven your constitutive model. Yeah. So here, so this is the real easy DSL that we provided for you to model such a probabilistic nonlinear modeling, and we are considering the uncertainties in the HA and the CR, and the d epsilon, the incremental strain, will be automatically from the global displacement increment. Yes,
And
Professor.
if I may say, the epsilon and sigma, they're all uncertain, but we provide distributions, probability distributions for two material parameters, HA, which is the initial stiffness, and then CR, which controls HA over CR controls the shear strength in 1D. This all works fine in 1D.
Yeah.
In 3D, questionable. Okay, go ahead.
Yeah, and so as you can see here, so here we need to provide the following inputs to this command. Obviously, you need to specify the material ID, and also you need to specify the ID for the triple for triple product. So if you looks our previous theoretical lecture, yeah, you're going to see that for a constitutive probabilistic modeling, it's very important to provide such a triple product so that we can perform the Galerkin projection to identify what the incremental polynomial chaos coefficient of the stress and also the stiffness. And then obviously you need to define, sorry, you need to define a a random variable for your two uncertain parameters HA and CR, and also you need to specify the units for the HA because as we mentioned before, here the HA when we define them as a random variable is unitless, and actually
Yes.
The unit for HA would be a Pascal. So
Well, it can be Pascal, but can be
yeah,
other stuff too. But in this case, I mean, it's a unit of stress, but you have to define what it is. I mean, you can define Pascal, you can define PSI, whatever you use.
yeah, that's true. Yeah, that's true. Yeah. And so the definition of the random variable for the HA and the CR that you need to provide is the same as what we previously talked about. So today we're going to mainly talk about how do we define the triple product before we can define such a material model. So if you look at our previous lecture, so for this triple product, actually you need to define a third order tensor. So here is a phi I, phi j, and the phi k, and essentially is the expectation of the the third order tensor of the polynomial chaos, the triple product of the polynomial chaos basis. So here the phi I and phi j are the polynomial chaos basis of the uncertain parameters, material parameters, which is the HA and the CR. And here this phi k is comes from the another different polynomial chaos basis, which is for uncertain incremental strain, and this is to be the same as your global displacement uncertain polynomial chaos that you're using. So we need to define such a third order tensor so that the program can do the Galerkin projection. So here is um, how do we define them in the real easy. So first of all, in order to define such a triple product, we need to define individually how each polynomial chaos basis looks like. So here, this is the command that you can define the basis of the polynomial chaos. So you need to specify two parameters. One is the dimension of this polynomial chaos, the other is the order of this polynomial chaos. So for example, here I'm defining a random field with a polynomial chaos dimension 4 order 3 uh, um, the basis. So by default, if you just specify this command, actually you are essentially the fourth dimension would be epsilon 1 to epsilon 4. But in some cases, you might want to go to other dimensions. For example, you might want the dimension to be epsilon 10, for example, to epsilon 13. So actually, that would be a still four-dimensional order 3 polynomial chaos. But how do you define that one? So if we have the dimension that is not starting from 1 to the total dimension that you are specifying here, then you need to use another command to specify for each of this local dimension, dimension 4 here, what are the global dimension it's corresponding to. For example, you need to use this command, define random field Hermite polynomial chaos dimension from a single file. So this file will specify some information, tells you what this four dimension of this polynomial chaos basis corresponding to. And
And can I ask a question? And
yeah,
why would you want to define this as a different dimensions from not from 1 to 4, but from 10
because
to 14 to?
yeah, because they might have a different source of the uncertainty. For example, you might have uncertainty in the material parameters, have some uncertainties in the load, for example, the ground motion, right? So usually, for example, we can define, first say 4 dimension as the material parameters, the source of the uncertainty, and then you might have dimension 5 to dimension, I don't know, 100 to be the uncertainties in the ground motion. So when you do the triple product, you want to, specify them out, in a correct order, yeah. So can you see this like a little like a
Yeah, we
rectangular
see
box?
little
Oh,
frames. Don't worry. This is something with your screen. Don't worry. It works
okay,
fine.
okay, yeah. So so here, so basically, so here I show you an example. How do we define this? The not the by default dimension. Not from dimension order 1 to the dimension n that you are specifying here. So here again, I'm specifying dimension 4 order 3 polynomial chaos basis. But now I'm defining, I'm using another command, which is this command to specify how this local dimension looks like. So you can see here, you need to specify a txt file that contains the dimension information for this random field. So here, so basically on this txt file, you need to specify two columns. The first column is specify the ID of each local dimension. And then the second column is the corresponding global dimension corresponding to each local dimension. For example, here I'm specifying, the dimension should be dimension 10 to dimension 13 for this dimension 4 order 3 polynomial chaos basis. So yeah, so you need to be careful, what the source of the uncertainty that you are considering when you define this polynomial chaos basis. So
And,
after you, yeah,
I'm sorry. Can I to interrupt? Just we're gonna prepare examples in next few lectures after seismic motion lectures, and we're gonna go through these a little more.
yeah. So after you define those polynomial chaos basis, so then you can compute the triple product. So here, this is the command that you're going to provide the triple product. So is add the triple product. You need to have an ID associated with that, and then you need to specify the 3 IDs of the random field. This 3 ID of the random field essentially will tells the program which is the polynomial chaos basis associated with the 3 random field. So here, I just want to remind you that the order that you are specifying here is very important because this is the third order tensor, and it's corresponding to the index of this third order tensor. So remember, for the material modeling, we want the first first index to be the corresponding to the polynomial chaos basis of the material parameters. And the second is the same as the first, but the third polynomial chaos basis is actually corresponding to the uncertain incremental strain. So should be IJK in this way. Um, this command will directly compute the triple product and add to the domain of the analysis. But usually, when you compute the triple product, actually it's a very time-consuming operation. Say if you have if you have a thousand of polynomial chaos basis, so the computation of the triple product sometimes can take a lot of time. So usually we can in practice, what we can do is we can use this command called generate the triple product, and then we're going to write this triple product information essentially is a third order tensor into a HDF5. And then, next time when you want to use the same, polynomial chaos basis, you can directly load this HDF5 so that you don't need to compute the same thing again and again. So this is the command that you can load the triple product from that generated HDF5. So there are two ways that you can do that, but we recommend you to go with the second way.
Yes, you essentially save a lot of time. You pre-compute those, and they're not going to change. They're essentially triple products of basis functions, and so those don't change. And so,
yes.
And I think we're going to prepare a number of those to be included so that people can use them.
Yeah, that's true. So here just to show you a little bit more detailed format that the triple product HDF5 format that you're going to see. So essentially we got the first three part is show the basic information that for you to check whether this is the polynomial chaos basis that you are asking for. So for example, the first three data set will characterize the information for the polynomial chaos of the PC1. So here, if you open this PC1 dataset, it's going to be a 2D array, and each column of this array will containing the order corresponding to the different dimension of the polynomial chaos basis. For example, here I'm looking at the fifth polynomial chaos basis. Here I got a 1 and 1, which means it's the first order of dimension 1 and the first order of dimension 2. So essentially that you can think about this is a KC1, KC2 for the polynomial chaos basis. And if you look at the last one, which is the last polynomial chaos basis, it will have 0 order for the dimension 1 and the order 3 for the dimension 2, which means it's the third order dimension 2 polynomial chaos basis, which would be KC1 cubic minus some minus 1 some stuff. Yeah. So that would be, yes, Professor.
So we're going to make recommendations for these. People will not really need to go through these details. We're going to prepare some things for them so they can run these examples.
Yeah.
But it's good to know. It's good to know what's behind this.
Yeah, and similarly, you can check, what's the dimension information, and also the variance is correct or not. And so once you check all those information, if you want to know the triple product actually is stored in the last four data set. So because the triple product is usually a very sparse a set order tensor, so we store them in the sparse representation. We only store the non-zero component of this third order tensor. So here I specify here, for the last three data sets, going to specify the non-zero index of the component, and the real non-zero element of this triple product is contained in this triple product data set. And I mean, if you just want to use them, you don't need to go this deep, but just for your information to maybe you want to check, whether this triple product is correct or not. Yeah. So once you have all those triple product information, you can so here just to show you an example for you how to compute a triple product. So here I define two polynomial chaos bases. One is for dimension 2 order 3, and the other is dimension 3 order 3. So then I can compute this triple product as using this command, add a triple product with Hermite polynomial chaos from the random field 1, 1, and 2. So that will compute the triple product corresponding to this different basis of the polynomial chaos. And the later part is just a version that where you will first generate a HDF5, and then you will load this HDF5 to add this triple product to the domain of your analysis. So once you define those triple products, then you can go ahead to define this material parameter, the stochastic material. So so here you have, so here actually in real easy, we provide two different DSLs. So the first one is the by default version. As you can see, the only difference, the second one in the showing below is that more gives you more advanced control to the number of the polynomial chaos terms that you can use in the constitutive modeling. So essentially, if you just use the default version of the probabilistic constitutive model, um, it will use the four dimension, the four polynomial chaos bases that you are specifying in the triple product. But sometimes, in order to, for example, you want to save some computational resources, or you want to, do some truncation in the constitutive modeling, you can specify how many orders you want to use for each of these different uncertainties. For example, uncertain HA, uncertain CR, and uncertain incremental strain. And sometimes we do see people, for example, they will just use the mean strain to the constitutive modeling. So you can just say save the number of polynomial chaos terms for incremental strain to be 1. That will just consider the mean for the probabilistic modeling. Yeah, yes, Professor.
And so one thing is to actually define higher orders and higher dimensions, and then try to reduce, and then maybe compare results and see which lower order, which more computationally efficient model does the job. This is the idea.
Yeah, because for sometimes, this higher order terms, they just not contribute to the result much, so you don't need to go the 4 dimension.
But it's okay to define all the way and then reduce to see which one actually still gives you good results, and then go with that, because it's much more computationally efficient.
Yeah, that's true. Yeah. So yeah, this is just to provide you more flexibility for what you want to do. So then, once we define all those information, we can go ahead to define such an example for the stochastic, Armstrong-Frederick material. So here we already defined the previously we already defined the triple product, and here I'm just showing you how we define the material parameters. This is the same as what we do for the elastic material. How do we define the modulus? Again, you need to define the marginal distribution, and then you define the correlation. So here I'm assuming HA and CR are uncorrelated, so because they are two different parameters, so I use a 0 correlation. And then you need to do you need to perform polynomial chaos Kaplan-Loiv expansion for these two different parameters, and then you can define use them to define your stochastic Armstrong-Frederick material parameters. And here I use the default version. I do not specify any truncation for the polynomial chaos terms. Yes, Professor.
So essentially, I mean, don't call it default version. I mean, there's really nothing default. You essentially use the one command, one DSL, and there's another one where you can actually reduce these expansion orders just to see how it works. But go ahead.
Here I'm just showing you the probabilistic behavior of this material, how it behaves. I think here for the string increment, we also consider the uncertainty with 20%. So here you can see that now you will have some both the uncertainty in the initial stiffness, because they are come from the HA, and also some uncertainty in the plateau for the strength. Yeah. So yeah, in the next, we're going to talk about how do we apply those probabilistic constitutive modeling to some realistic wave propagation examples, and also we'll show you how. Yeah, yes, Professor.
So essentially, what you're seeing here is a probabilistic response. There's a full PDF of this. What we're showing is essentially only the mean and mean plus minus standard deviation.
Yes, that's true. Yeah, so also all those stress will be represented in the polynomial chaos, and with this polynomial chaos, you can post process any statistical properties you want to look at. Yeah.
And remind me, what was the distribution for HA and CR? Can you go back to show me what was the distribution?
This is the
it was log normal. Okay, log normal. Good.
Yeah.
Good. Okay.
Yeah.
Well,
so we will stop here. Yeah.
Well, acknowledge people here.
Oh yeah, definitely. Yeah, this work was I had some collaboration with my collaborators, and also especially Professor Wang now in Tianjin University, and also those funding resources. Yeah.
Thank you very much.
For more information, you can go to check our website. Yeah.
Yes, thank you very much. So we'll stop here. Let me stop recording and announce that we're gonna do more in next few days, and we're gonna post this. So let me stop recording.